like 1 month ago. And then, yeah, I'll start a postdoc in China in 1 week. And then I'll be presenting today some work that we have done recently that connects the ideas of emission amplitudes with the idea of self-energy, which provides contributions to the two-body problem. All of this is within non-relativistic general relativity, okay? So this name of the talk is precisely the name of the paper. And we'll be presenting something very interesting that we could find in some of these processes, these emissions processes, which present anomalies, even though we are talking just at the level of classical amplitudes, classical processes. So within non-relativistic general relativity, we are talking about the bound binary system dynamics. And then in this case, first of all, we are talking about the in spiral phase evolution of the system, of the spiraling binary system. And then in this case, we work within the post-Newtonian approximation, using some of the important scales of the problem. First of all, because of the viral theorem, we can connect powers of G Newton with powers of V squared. But also, one of the scales, important scales of the problem, is the size of the object, which is characterized by the Schwarzschild radius, if we are talking about black holes. And the other scale, the other important scale, is the separation between the two bodies, okay? And finally, the other scale of the problem is the wavelength of the gravitational radiation, which is connected to both the velocity and the radial separation of the separating the distance between these two objects. And because we are talking about the bound problem, all these scales are connected. We can see at the middle of the, sorry, I cannot use the, okay. We can see here how they are related. And then if we are considering a non-relativistic regime, so we are considering V to be much smaller than the velocity of the light, speed of light, we can finally arrive at this hierarchy of scales, okay, which allow us to split the problem, okay? And then, in particular, this allows us to use the method of regions to build different effective field theories. The first one, this is accomplished by splitting the metric perturbation into potential modes and radiative modes. These modes, the potential modes are off-shell modes scaling with momenta scaling like this, while the radiative modes are on-shell modes, so gravitational radiation. And we can study different regimes of this problem. For instance, if we neglect radiative contributions, we can study just the potential contributions, whose dynamics can be studied just using these potential modes, which are the modes that provides the gravitational binding between the two objects. Here we are more interested in the far zone section of the problem, which is this regime of the gravitational waves, in which the wavelength is considered to be much bigger than the radial separation between the two bodies. And in this case, we are studying the gravitational waves emitted by compact systems, okay? In order to build the effective theory in this case, we start from a fundamental theory in which we have these two modes, and we integrate out these modes in the so that we arrive at so we have this effective action, okay? We have the effective action that describes how the two particles they interact with the gravitational field, and we are studying all these dynamics within general relativity. So we have the Einstein-Hilbert action plus a gauge fixing term. When we integrate out the potential modes, we arrive at this effective action, okay, which couples the energy momentum tensor to the radiative modes. And then we can perform a multiple expansion, which is just we expand in powers of r, this radial separation between the two bodies, over the wavelength of the gravitational wave. By doing this effective action goes to this multiple expansion, as it was presented in 2010 by Goldberger and Ross. And in this case, again, we are considering binary, we are considering compact systems. These multiple moments that we have here, we have a whole series of multiple moments. They encode the physics of the internal physics of the problem. So we can talk about a binary system or more general compact system, as long as the wavelength of the radiation that the system is emitting is much bigger than the typical size of the system. These multiple moments, we have two series. One series which is which has electric parity, and the other. This series here is electric one, which is connected to the electric part of the Riemann tensor. And then this is the magnetic multiple moments, which are coupled to the magnetic type of the Weyl tensor. We also have a coupling of the energy of the system, and we also have the angular momentum of the system. Okay. In particular, we can use this effective action along as the Einstein-Hilbert and plus gauge fixing term in order to compute processes, in order to compute emission amplitudes, which are represented here by this A here. And from there, we can compute gravitational wave observables. Okay. In particular, we can compute nonlinear processes. So this is the simplest of the nonlinear process that we can consider, which is called the tail process, which is basically the scattering of radiation emitted by these multiple moments, this system, which gets scattered by the static potential of the source, generated by the energy of the system. We can also study more complicated, more nonlinear process. We have already done that in one paper 2 years ago, in which we investigated this kind of process, which is the tail of tail, which is basically a generalization to higher order of this process, in which the gravitational radiation is scattered by the static potential generated by the energy of the system. And this is just one of the types of diagrams that we are interested in studying, emission processes, emission diagrams. But also, we are very interested in studying also these kind of diagrams which do not possess a external graviton going out of the system. But by computing this process, we are able to obtain contributions from radiative nature to the conservative dynamics of the system. So when we go, if we
are these diagrams related to the crystal memory?
To what?
Nonlinear memory, like crystal memory?
Yes, it's precise. It's connected.
How is it?
Okay. So the nonlinear memory, instead of, so we have here, so we have, for instance, this diagram. It's the gravitational wave scattered by the gravitational field generated by the static, like Newtonian potential of the source. But the nonlinear memory is the this corresponds to this diagram, in which you have gravitational waves being scattered by gravitational waves. And we are very interested in studying also this kind of processes.
So
but I'll talk a little
so
bit.
the one is the onshore one is dot.
Okay, these dots, it's, okay, sorry. It's because these are on-shell modes. These are gravitational waves themselves. And these are the static gravitational field generated by the mass of the system. Yeah, like the potential, the Newton potential, sorry. Okay. Okay, so besides the conservative contributions that we obtain, if we consider just the potential modes, okay, we also have processes coming from radiative nature, which also gives contribution to the conservative dynamics of the two-body system. And we are very interested in studying this. And these are the diagrams these self-energy diagrams, they are the ones that we need to compute in order to take into account these conservative contributions coming from radiative processes, okay? Which represents gravitational waves being backscattered back to the system and affecting the dynamics of the two-body, okay? In the paper that I'll be talking about in this presentation, one of the things that we could study is the relation between this kind of process, this kind of diagrams, emission diagrams, and this kind of closed self-energy diagrams. Okay. So just to be definite about what is the system that we are considering. Again, we are considering compact systems in which the wavelength of the gravitational radiation is much bigger than the typical size of the system. And in this case, the system can be described by this effective action, which has this whole series of multiple moments. In this case, these coefficients are given by these expressions here, okay? And again, the multiple moments are the actual sources of gravitational radiation. So if we consider R equals to 0, we are talking about the quadrupole moment. And we have the octupole moment for R equals to 1 and so on. And also, we have again, the energy and the angular momentum of the source here. Again, we are not considering anything beyond general relativity. And the gauge that we use is the harmonic gauge defined by the Christoffel symbol in this contraction, okay? And this is the gauge fixing term in order to be able to perform perturbative computations. So one of the most important quantities that we want to talk about is the one-point function that will describe the classical gravitational field. So in all these diagrams that I presented, they are classical. They do not have quantum contributions, especially because we are considering that the source is very heavy compared to the gravitons that it's being exchanged. And we want to compute the trace reverse part of this quantity defined using this expression here, this projector. Because by computing in general processes, general nonlinear processes, we'll have that the one-point function will be given by an expression like this, okay, in which we are able to define the gravitational scattering amplitude for the expression that we find here. This is the most important quantity in this talk, because we will be analyzing things like the word identity and consistency for the amplitudes of the process that we are interested in studying. In particular, if we go back in this expression and write it in direct space, it's written, can be written this way, in which we can see that basically the inverse Fourier transform of these scattering amplitudes that we are considering, it's just the energy momentum tensor. That's the connection between these amplitudes and the energy momentum tensor of the gravitational field. So we will be notice that if we contract this one-point function with the for divergence, we obtain this expression. Okay, and then notice that if we have this expression vanishing, we naturally have that the Lorentz condition is satisfied, and also the conservation of the energy momentum tensor is also satisfied. But notice that the gauge that we have been using, that we are actually using, is not the Lorentz gauge, which is defined by this expression, but rather this expression here. It turns out that if we consider leading order processes, this expression, this gauge condition, becomes just the Lorentz one. Okay. However, if we consider higher order processes like the tail of tail, and the memory, for instance, on the right hand side of this expression, like here, we have lower order processes contributing to this expression. Okay. For instance, if we have processes of second order in G Newton, there will be terms here of first order leading order. However, we could show, it's easy to show actually, that if we follow this nonlinear process of higher order, this quantity here is proportional to omega square minus k square, so that if we consider this process to be on shell, we actually go back to this expression, to the Lorentz condition, the simple one, and then we arrive at also at this kind of thing, which is precisely the word identity. In other words, if we compute these processes on shell, we want the processes to satisfy the word identity. And these on-shell amplitudes, they can be used to rewrite the waveform far away from the system, which is given precisely by the on-shell expression of these amplitudes. So we want to use this framework in order to compute from the simple amplitudes and analyze all these relations, and to see if they satisfy these conditions and so on. Because as we will see, for some high order processes, this will not be automatically satisfied, and we need to be able to solve this problem. So we start by computing leading order processes, which let me draw here, corresponds just to having this simple emission. Okay. In particular, we can compute the gravitational waves emitted by the multiple moments this way, but also we can compute we can compute the gravitational fields generated by both the energy and the angular momentum of the source. Okay, that's what we do here in this first line here. We put here the solutions, and if we test whether or not the Lorentz gauge condition is satisfied, we see that in direct space this is 0 if we consider, provided that the energy and the angular momentum are conserved. So in linear order, we need to consider that the energy and angular momentum of the sources are conserved. Here we have these amplitudes computed for generate multiple moments of both parities, electric and magnetic. And again, if we try to see if the word identity is satisfied, we see immediately, using the expressions that we obtain, that they are satisfied. Okay, and then we move on to the next, the simplest, the next two leading order. in which the simplest process that we have is the tail that I presented before, which is basically this one, in which we have gravitational waves being scattered by the presence of a static mass or energy of the source. Okay. These are the expressions that we find, and in particular, we compute things in dimensional regularization because we find a divergence here. Okay, this is something that we have studied and studied the origin of this. I mean, we have studied the types of divergences that we encounter in this problem. Particularly, these are infrared divergences that gets exponentiated when we consider high order tails and can be removed. And then for all these multiple moments, so we can compute the theory effect for all the multiple moments of electric and magnetic types. We obtain these coefficients, these finite coefficients here, which is well known from computation done in traditional methods, in particular by Luc Blanchet, for instance, and Thibaut Damour. So we can reproduce this. In particular, if we investigate whether or not the amplitudes for these processes, they satisfy the word identity, we see that again, the word identity is satisfied for any of these processes, for any multiple moment of any kind of parity. And then we move to a analog process of this one, but instead of having the gravitational wave being scattered by the static potential generated by the energy, we substitute this by the angular momentum. Okay, and we want to investigate these kind of processes, and also again investigate whether or not this the energy momentum tensor is conserved and so on. And this is the expression that we find, at least for the TT part of the amplitude. Okay, and if we actually use the general solution, considering not only the TT part, but also all the other components, we can test and see that for the time component of the word identity, we have that they are satisfied. But we consider the spatial part, we have this expression, and this integral is proportional to Kronecker products of Kronecker deltas. In particular, if we consider the quadrupole moment, this is for the electric case. Okay, this expression gives a finite number, okay, and does not vanish in this case. So if we talk about this process, just for the quadrupole moment of the electric case, okay, we have this. We can see that the word identity is violated in this case. Okay, actually, we have already done this also for the not only for the electric but also for the magnetic quadrupole, and we also have this kind of anomaly. Okay, but as we will see, this anomaly can be removed consistently, so that we call this a consistent anomaly. Okay, and in order to
R is 0 is the radius or something. So no.
what?
Unless R equals 0.
Yeah, so if R is equal to 0, this is not present here. So the integral is just a number. Otherwise, if we have
the small r, unless R equals 0.
Yes, which corresponds to the quadrupole moment.
Yes.
Yeah, so R equals to 0 is the quadrupole, equals to 1 is the octupole.
Okay.
Parameterize the whole series of the multiple moments. And then again, if we have if we consider the quadrupole moments in both of the case, electrical magnetic case, we have some sort of anomaly. The word identity that should be satisfied is not. Okay, so that does not correspond actually to a solution to the problem, because as I told you, this should be vanishing in order for this solution to be consistent with general relativity. In this case of the quadrupole moment, of the angular momentum tail of the quadrupole moment. So in order to understand this, I will move to consider the Einstein-Hilbert equation, action plus the gauge fixing, okay? Basically, the structure that we have is given by here, by this kind of things. If we obtain from this action the equations of motion by around the action, we obtain something like this, okay, in which in this right-hand side we have terms quadratic in perturbation, cubic, and so on. And then we can study perturbatively processes in order of G, so that this is kind of a post-Minkowskian perturbation, okay? And then in particular for leading order processes, this is the equation that we need to solve, okay? So all these processes like these ones, they are leading order. If we consider tails and processes which have this kind of one loop here, we have to solve this equation, okay? And so on for higher order processes. In particular, we could show explicitly that if we take the solution that we have for this angular momentum tail, which presents this anomaly, and try to see if it is a solution to this problem, to this equation, we see that it is indeed. However, what's missing is that the solution to the problem is not just we have to not only solve these equations, but also at the same time we need to solve the equations for the gauge fixing condition. Okay, that's what is missing. And basically, what we are solving by computing perturbatively these processes is just the first of these equations. So just this equation, but we need also to to obtain solutions which are consistent with this equation as well. Okay, so what we do is notice that the solutions that we obtain in our process is a particular solution to this equation, but also we can add a homogeneous solution to this equation equals to 0 here, to be such that we want some solution and force it not only to be a solution to the homogeneous version of this equation, but also to kill the contributions that makes this not to be 0. And we can always do that. Actually, this is something done in traditional computations of this kind of process, done by Luc Blanchet, for instance. In particular, it is possible to show that if we take the full divergence of this equation on both sides, this is immediately 0. And then, because we are solving here, in this case, the homogeneous solution to this, it is always possible to find a general solution to this quantity here, okay? Parameterized by 4 sets of STF tensors, symmetric and trace-free tensors, to be such that this solution that we want to add satisfy the homogeneous solution, but also it is such that it kills precisely the excess that the particular solution has, which makes the solution not to satisfy automatically this part here, okay? And that would be the solution to the full problem if we add the particular to the homogeneous solution like this, okay? So we borrow here things analyzed and things studied in the traditional computations, especially by Luc Blanchet. And a full solution to this homogeneous equation here can be translated into our kind of amplitudes. So I defined here this h mu with by this contraction to the amplitudes of our processes. And these are generic solutions to the wave, to this homogeneous solution that we want to add to solve the anomalies that we are faced. In particular, they are parameterized by these four multiple moments, okay, N, P, Q, and R. And then, so we want to define amplitudes that correct, okay, the excess of our original amplitudes to remove this violation of word identities. So these are precisely the little ways which plays the role of the homogeneous solutions in direct space. These are solutions to these expressions here. If we want to obtain some little way that cancels the anomaly in these expressions. And in particular, if we go back to our case of the electric quadrupole moments in this angular momentum tail, these are the only multiple moments that survive in this expression that when we compare our let me show here, when we compare this anomaly here, okay, this leads to just these two multiple moments. Then we can plug them here in this expression, all of the others being zero, and we find that these are the correcting amplitudes that has to be summed to the original amplitudes that we computed in order to provide actual solutions of general relativity. So we do this for the only two processes that present the anomaly. Related to this process, the angular momentum tail for both the electric and magnetic quadrupole moments. Okay, and then we finally obtain a. If we go back to direct space, we can we precisely obtain solutions presented in traditional computations. And again, these little a's here represent these homogeneous solutions. If we go back to direct space, okay, they play the role of the homogeneous solution. Then, before continue, let me move on to something a little bit different. So we have been talking about just the emission amplitudes that we have that we are interested, but then let's go to this kind of amplitudes that I presented, which are the self-energy, which do not possess these external gravitons. Okay. In particular, if we consider the leading order process of this self-energy, which is characterized by this interaction of two electric quadrupoles, and compute by usual ways this contribution. These are the expression. This is the expression that we obtain. We can rewrite this in terms like this expression by noticing that this expression that we find in here is just the sum over polarizations of the gravitational field. Okay, and then again we can rewrite this in terms of this integral here, in which we have these two amplitudes. So basically, this provides a way of telling us how to use emission amplitudes, these ones, like a product of these two ones, and connect them in order to compute this kind of closed diagrams that are important.
I have a question for you. So in the previous part, so I'm not very familiar with this. So is this result for the tails that you are obtaining from the software? Is it like this blue shifted result, including this new gauge condition?
So they
so it's already been obtained.
Okay. So
for the first time.
So all these analyses that we have been done, no one had never done before within this context, but it's well known from traditional computations, not using effective filter approaches. Actually, for all the mass tails, people have already computed, so we could reproduce their expressions. But actually, for these processes involved in this angular momentum tail, it's an original computation. So basically, in traditional computations, people have computed just the first of this process, involving just the electric quadrupole moment. But we have computed this process for arbitrary multiple moments of both electric and magnetic polarities. But just the quadrupole moments of both polarities present this anomaly. The other ones, from octopole and on, they do not have this problem because of what we saw in this integral here. This is consistent with the word identity whenever we have a octopole and on for both electric and magnetic. Okay, so more generally, if we consider more complicated processes, not only this leading order, so we have, let's say, more complicated interactions here and here. We can also build this kind of diagrams by connecting these two legs, as we have learned here. Particularly, if we have two processes and two amplitudes, one for each of these processes, we can compute the self-energy obtained by the connection of these legs, just by writing the amplitudes here connected by the propagator in the middle of them, and integrating over the momentum K that we have in the diagram. Okay. So we use this in order to, first of all, compute the tails, the simple tails, the mass tails, from emission amplitudes. So consider again that consider that we have this process, the tail, in which we have the energy here, the series of multiple moments of any multipolarity, and we have one single leading order process here. We can use these two amplitudes to compute this kind of diagrams, in particular the one corresponding to the simple tail. So we can compute this kind of diagrams for any multiple moments here. Starting from these emission amplitudes. Okay. And in particular, if we have amplitudes which are analytic in K, we can take just the on-shell part of them. That's something that it's not difficult to show. We did that from the previous computation, okay, for the simple tail, connected in this way with the leading order emission, and we obtained precisely the solution, the result that we have already obtained this before. By doing this, we can connect the finite coefficients of both types of diagrams, and this is what we have for the electric case. So this is the coefficient that we have presented before, obtained before for the this kind of emission processes, emission diagrams. And this is the finite coefficients that we have in these self-energy diagrams that again are important because they provide contributions to the conservative dynamics of the two-body dynamics. Okay. In particular, the simplest of these diagrams, which corresponds to plotting here the electric quadrupole moment and the electric quadrupole moment here, they are important because they provide the first contribution to the the first radiative contribution to the conservative dynamics, which enter in the fourth post-Newtonian order, okay? And that's the only diagram that it's present in this order. When we move to the 5pn order, we not only have also to consider the quadrupole moments here in this tail, in the electric case, but also we need to consider the octopole of the electric case and the quadrupole of the quadrupole cases. And also the importance of the biggest importance of this research that I'm presenting is because another type of process that enters the 5pm order, similar to this one, is the one for the angular momentum theory. So when we have the electric quadrupole here, and instead of the mass, we have the angular momentum. And because we found an anomaly in these processes, we expect that when closing the diagram in order to build this, we need first to correct this emission diagram in order to obtain the correct contribution to the conservative dynamics coming from this process. So we did that for the electric, for the mass tail, for both parities, for all the multiple moments, and this connection matches previous results. But also we want to do this for the case of the angular momentum theory. Remember that the only problem that we face with this process, the angular momentum theory, was when we consider just the quadrupole, the quadrupole moments of both cases. If we consider the octupole alone, they do not present any problem, and then we can use this kind of diagrams, emission diagrams, connect to leading order processes, and obtain the correct contributions to the these kind of self-energy diagrams. However, again, we cannot use the original computation of this process for the quadrupole moment because they present an anomaly. And then if we close the diagram in order to build this kind of process, we will find something which is not consistent with general relativity. And indeed, if we do this, what we obtain is precisely what has already been obtained in the literature by the direct computation of this diagram. But we now believe that this is incorrect because the sub-amplitude is not consistent with general relativity. So the correct thing to do in this case is, first of all, we compute emission amplitudes. We correct them whenever they present this anomaly. And then we close the diagram in order to obtain the correct contribution for the conservative dynamics of the two bodies. We did that in particular because the octupole case do not present this anomaly. We could obtain this self-energy by the two different ways, by direct computing this amplitude and by gluing this amplitude to the leading order, and these matches the two different results. But then we, for the electric quadrupole, we obtain this new result by doing first correcting this amplitude and gluing them afterwards. And this result was recently obtained also by traditional methods. So we trust that this is the correct answer for this process, which again is important because it enters the 5pn order, which is basically the order in which we are interested in closing right now, at least for the spinless case. In previous computation, instead of this 1/30 minus 1/30, it was this different number, okay? And one interesting thing is that this is not particular of this kind of this angular momentum tail process, but also we could already see that this is also present in the memory process, which is also one of the one important process that enters also the 5PM dynamics, and we need to afterwards study this separately. But then in this case, we find problems, especially because the emission amplitudes, they are not analytic. Okay. And then there are some technical things that we still are investigating. And then, so in this case, in this presentation, we have studied, first of all, emission amplitudes for the leading order processes, but also for the tail, the simple tail, the mass tail, and also the angular momentum tail. Okay. In particular, we have identified this anomaly that was never observed before in this context, in this effective approach. We provided a fixing based on traditional methods presented by especially Luc Blanchet. And in particular, we could not only study this kind of process, emission process, but study how this can be used in order to compute self-image diagrams, which in this case becomes very important in order to fix the anomaly before closing the diagram and obtaining the correct contribution to the conservative dynamics in the two-body case. Yeah, that's very important, in particular for the 5PM completion of the two-body dynamics, because because of this kind of anomalies never observed before. And yeah, that's it.
Failed tail just means there's no divergence, but there may be a bias apart.
Yeah, so it's failed tail because tails are characterized by these non-local contributions. In the case of the mass tail, we have this because it presents in particular the divergence, which gives rise to a log. Okay, but then in this angular momentum case, we just have a local contribution. But we still call tail because they have the same topology, the diagrams. And that's it, just that. So it's fail because it doesn't present the thing that characterizes the tail. Yeah.
Is there an understanding why this anomalies arise?
Okay, so that's precisely what we have been discussing lately here, because we still do not understand the physical meaning of this. Yeah, we just was able to identify that indeed in the way that people are used to compute things, it's not fully consistent. That has to be very carefully analyzed before taking this as granted. And yeah, and we also provide a way of correcting this at the level of these amplitudes, but still we do not have a reason why this is happening. Yeah. We want to.
We should have a reason why this is not almost never happens.
Yeah.
Yeah.
Yeah, that's something that we.
We're not solving the equations.
Yeah, that's something that made us very confused because at the end of the day, all the solutions that we have, including the original solutions that we obtained for these processes that present the anomaly, they are consistent with the solutions of the problem that we obtained by varying the Einstein-Hilbert equation, Einstein-Hilbert action. But the problem is that these solutions, they are not consistent automatically with the gauge condition, and we do not know why the other simple processes, they satisfy not only the equations of motion, obtained by the action, but also the gauge condition equation. That's something that we are still figuring out.
Question. So the previous last slide, you had a different number for the energy for the angular momentum. That was without correcting the anomaly, this 8/15.
So basically, if you blindly compute this kind of process using our effective filter approach, you obtain for this particular process here, the angular momentum fade tail, you obtain this 8/15. But there's no way of testing whether or not this is correct. Okay. But then we could see that if we compute this emission amplitude, the original one, and we connect to this leading order, we glue them, we obtain precisely this 8/15. But then we now know that this is not the only thing. This is not the only piece that is the solution that corresponds to this actual solution to the problem. We also need to add this homogeneous solution to make this consistent with general relativity before gluing to the leading order and then obtaining this 1/30, which is the correct contribution. Hi.
There is a way of testing the needed. There are no momentum flux.
Yes, I forgot to put it here. Yeah, I'm really sorry about this. We could, yeah. So after obtaining this this 1/30 from this diagram, we can complete from this the angular momentum flux of this process. And also we have another way of computing this quantity. We have two ways, one from the self-energy diagram and one from traditional computations using the waveform for this process, the Hemisphere, actually the HIJ TT. And we have a match for the we have a match for this quantity obtained from this and from the other type of computation. So that's a important consistent check that that I forgot to put it here. Yes.
No. Can this be or not? Problem of negatives. Yes, how you
yeah, we still do not know. But the thing is that we cannot do perturbative computations without putting some gauge fixing, and we put actually the most natural one. So I don't think that's the problem, but we still do not know. We are investigating.
last chance?
Gabriel again. Take the cloud every 10 here.
Yes, upstairs. As the top floor. Above, one floor above.